So how do we find the length of arcs and the areas of sectors? And this is where radians is going to help us. So we have our circle, and of course we know the circumference of a circle, 2 pi r, and the area of our circle, pi r squared. But what happens if we just want a piece of that circle? So I'll just draw in a sector here, sector AOB. Now AB is what we of course call an arc. In fact, there's actually 2 arcs there. There's the minor arc is the small one, and the major arc being the large one. Let's say the angle at the centre there is theta. Now we want to find L, the length of that arc AB. We can work out what fraction of the circumference we have based on the angle at the centre, and what fraction that is of the 360 degrees. However, in this case, we want it in radians for this to work. So the fraction, theta, measured in radians, divided by 2 pi, because there's 2 pi radians in a complete circle. That's the fraction of the circumference that we have. Now, nicely, the 2 pi cancels, and we get a neat little formula that the length of the arc is equal to the radius times the angle at the centre. But that angle must be measured in radians for this to work. The length of an arc, L equals r theta. Now, we can do the same thing when we want to try and find the area of the sector, OAB. And once again, we've actually got 2 sectors there. We've got the minor sector, the small one, and the major sector being the large one. So the small one, the angle at the centre is theta. We want that fraction of the whole area. So the pi's cancel in this case, and we get a half r squared theta. Once again, theta must be measured in radians. The area of the sector, half r squared theta. All right, well, let's just do a simple little example here. We've got a circle. Now, I've deliberately made the angle at the centre there in degrees to highlight we got to convert it. So if they give us it in degrees, we need to change that to radians. So length of the arc AB, r theta, 5 times the angle at the centre, not 45 degrees, but pi on 4 radians. And so there's the exact value, 5 pi on 4 centimetres. The area, half r squared theta, so half 5 squared times pi on 4, and we get 25 pi on 8 centimetres squared. Another thing that we could be interested in finding is finding not the area of the sector, but the area of the segment. So if I draw in the chord AB, the segment is that piece of the circle that the chord cuts off. Again, there are 2 segments there. The minor segment is the small one that I've shaded in, and the major segment would be the other bit. So to find the area of the minor segment, well, what we can do is we can find the area of our sector, but then take away the area of that triangle. And you remember the formula for the area of a triangle? Half AB sine C? Well, for ours here, it's going to be a half radius times the sine of the angle at the centre. So a half r squared sine theta. We've got a common factor there of half r squared, and so then we just have to find out what theta minus sine theta is. And so summing in all the values, we get quite an interesting answer. It's an exact answer, 25 pi root 2 minus 100 all over 8 root 2 centimetres squared. Yeah, we probably would want to do a decimal approximation in reality, but I'll just leave it as an exact value here. Let's try some of those in 11i.